The tropics of Mars are commonly littered with small, bright ripples that were somehow shaped by the wind. Called transverse Aeolian ridges or tars, the features stand up to 6 meters tall and are spaced a few tens of meters apart. They are typically oriented transverse to modern-day wind directions and often found in channels and crater interiors. The physical process that produces these features is still mysterious. Most tars display no evidence of internal structure, so it is difficult to discern exactly how they were formed. Some rare banded tars have also been discovered in an area south of Syrtis Major, which is an old shield volcano with a central depression that is elongated in north-south direction. These features resemble tars elsewhere on Mars, except that they show bands of layers on their northwest faces but fewer to none on the southeast sides. One possible interpretation of this strange layering is that these particular tars are made up of wedge-shaped layers. If this hypothesis is correct, it implies that the ripples grew vertically over time as material accreted at the crests of the ridges. It also suggests that the banded slopes faced upwind. This observation might provide a valuable clue to the formation of tars elsewhere on Mars if they have a similar internal structure, but that structure cannot be seen because they were made up of homogeneous materials that are uniform in color. This outcrop caught the interest of scientists when it stood out in images taken during Curiosity's exploration of the Yellowknife Bay area. The outcrop, which is about 20 inches high, stands out for two reasons. First, it forms a small cliff which offers a sense of how a rock unit differs from bottom to top. Second, the outcrop is full of holes. Holes form in rocks by diverse mechanisms. Identifying which mechanism can provide understanding about the rock and its history. If you look closely, you can see that the upper and lower parts of the outcrop differ, as the upper part has more holes and is more resistant to weathering. The holes here range from smaller than pea size to larger than golf ball size, and they are circular to elliptical in shape. Some of the larger holes have raised rims, as if the material immediately around a hole is slightly more resistant than material farther from the hole. At the right-hand end of the outcrop are a few stones that look as if they could have fallen out of the holes in the rock face. At least one of these looks like a thin, curved lining that could have coated the interior of a hole. Embedded nearby in the rock face is a larger, rounded rock that has a rock lining around it. Scientists are considering diverse geological processes, both igneous and sedimentary, as explanations for the holes and other characteristics of the outcrop. Igneous rocks commonly have holes called vesicles, which are frozen gas bubbles left over from when the rock was molten or fluidized. However, it is also possible to create holes in sedimentary rocks. The easiest way is for pebbles or cobbles in the rock to fall out as the rock erodes, leaving holes in the remaining rock. This is more likely to occur if the pebbles or cobbles are much harder than the surrounding rock. Holes in either igneous or sedimentary rock can later be partly or wholly filled with sedimentary minerals delivered by fluids or gases. The secondary minerals that fill the holes are sometimes harder than the host rock, so that when the entire assemblage starts to erode, they remain behind as round nodules. Geodes are an example of this process. This full circle panorama shows the terrain that surrounded Opportunity rover while it was stationary for 4 months of work during a Martian winter. The rover angled its solar panels toward the sun low in the northern sky during the southern hemisphere winter. Opportunity's tracks can be seen extending from the south with a turn in place and other maneuvers evident from activities to position the rover at the location. The tracks in some locations have exposed darker underlying soils by disturbing a thin, bright dust cover. Other bright, dusty deposits can be seen to the north, northeast, and east. Curiosity rover drilled this hole to collect some sample material from a rock target on lower Mount Sharp. The diameter of the drill hole is slightly smaller than a US dime, and the rock powder from the collected sample was subsequently delivered to a laboratory inside the rover for analysis. The site was chosen for sample collection because Curiosity had detected unusually high levels of silica and hydrogen in the area. Every winter, a layer of carbon dioxide ice or dry ice condenses in the southern polar region of Mars, forming a seasonal polar cap less than 1 meter deep. Early in the spring, the ice layer begins to sublimate, going directly from a solid to gas from the top and bottom of the ice layer. Under the ice, gas pressure builds up until a weak spot in the ice layer ruptures. The gas rushes out, and as it escapes, it erodes a bit of the surface. Fine particles are carried by the gas to the top of the ice and then fall out in fan-shaped deposits. At certain times in spring, fans of dust take on a gray or blue appearance. This view shows a region called Inca City where such phenomena was occurring at the time. The region has a series of distinctive ridges, and on the floor between the ridges are radially organized channels called areniforms. The channels have been carved in the surface over many years by the escaping pressurized gas, and every spring they widen just a bit. On the ridge at the top of the image, fans have lengthened and now look more gray than the blotches on the areniforms. At the bottom of the image, they are distinctly blue in color. Two theories have been suggested for the phenomena. Perhaps fine particles sink into the seasonal layer of ice so they no longer appear dark, or maybe the gas that is released from under the ice condenses and falls to the surface as bright fresh layer of frost. It is quite likely that both of these theories are correct.